Welcome to review recording 1A and B. To accompany recordings 1A and 1B, the instructional recordings, for Section 2.3 of Mathematics 2200. We'll be using the sine law to find angle and side measurements in non-right triangles, and we'll be solving a problem involving the ambiguous case. In example 1 here, we're told that angle y is 22 degrees. We're told that WY is 4.5 units. We're told that WX and WY are the same, so that makes this side here 4.5 units. The two sides are equal, so that makes it an isosceles triangle, making this angle 22 degrees. Now, based on the given information, we had two sides and an angle, SSA, making us think this could be the ambiguous case. But it's not, because, first of all, we have a diagram given, so there's only one case to consider. The other reason is we now know angle, angle, side as well. So we can apply the sine law because of that reason, which is not an ambiguous case. Let's find angle W. Angle W is equal to 180 degrees minus the two 22-degree angles, which gives us 136 degrees for angle W. So we could also say now that we have that much information, we've got angle, side, angle, if we wanted to use that reason for choosing the sine law. We'll write out the sine law. So if we recognize that segment XY is actually lowercase w for our formula, that's what we need to find, and we substitute in all of our angle and side measures that we know, we won't need to use one of these first two. So we'll just work with these two. A little bit of cross multiplication and whatnot. We've got W sine of 22 degrees equals 4.5 sine of 136. And then I divide both sides by the sine of 22 degrees. And that gives me approximately 8.3 for W. So C is our answer. Example 2. A cycling organizer maps out a triangular route where C, lowercase c, is 11 kilometers, lowercase b is 7 kilometers, and angle B is 38 degrees. Determine the number of possible triangles that exist. So because I don't know what the triangle looks like, I'll begin with just drawing two sides. C is 11 kilometers, that's my longer side. B is 7 kilometers. Now, if lowercase b is down here, that means angle B must be up here. So angle B is 38 degrees. We're stuck with that. It's an SSA case. And at this point, we don't even know if this triangle is even possible. This side here, for all we know, may not be long enough to meet this side down here. So I've finished labeling my triangle. Lowercase c is across from angle C, and I'll call this angle A right here. So this is lowercase a over here. It's an SSA case, so an ambiguous case. No diagram was given. So we've got to consider the ambiguous case, the donkey theorem. So I write up my sine law formula. Angle A and lowercase a we don't know. Angle B, we have sine of 38 degrees over lowercase b, that's 7. Sine of angle C, we don't know angle C, but we do know lowercase c is 11. A little bit of cross multiplication. We've got 11 sine of 38 divided by the 7. I won't bother to bring the 7 over to sine C. Just leave it where it is. That's equal to sine of C. So we have decimal 9675 approximately is equal to the sine of angle C. So inverse sine of decimal 9675 is what we have to do to get angle C. Now, I'll round to the nearest degree because that's what the problem used for angle B. So angle C is approximately 75 degrees. But that's an acute case. So we have to consider the obtuse case. So remember, an angle and a supplement always have the same value for sine. So our other possibility for angle C is 180 minus the 75 degrees, which works out to be 105 degrees. So we'll finish up on the next slide. I now consider my two cases. Angle C is acute. Now remember, angle B we're stuck with. It's 38 degrees. Angle C, the acute possibility was 75 degrees. Do we have anything left over for angle A? Yes, 180 minus 75 minus 38 will give us 62 degrees, so that's good. And the original sketch that I drew is pretty reasonable. Angle A would be around 62 degrees. The angle is not quite accurate, but these would be the three angle measures. I've adjusted the triangle slightly to make this angle look a little more like 62 degrees, and this one retains its 75 degree measure, and this one retains 38. Now in case 2, we're still stuck with angle B having to be 38. Angle C is 105 degrees. Does that leave anything for angle A? And indeed it does. 180 minus 105 minus the 38 gives us 37 degrees. And so the triangle might look more like this one. 105 degree obtuse angle. The triangle is nearly isosceles because these two angles are almost the same measure. And so we have two possible triangles. Key ideas: use the sine law to solve triangles when you have the angle side, or SSA cases. For the SSA case, the ambiguous case applies when there is no diagram, but if there is a diagram, determine if the acute or obtuse case is to be found.